this lecture, we're going to look at the multivariate Newton-Raphson method. Okay, so here's the statement of the multivariate Newton-Raphson method. Okay, suppose f from Rk to R is twice continuously differentiable. Suppose x is in Rk and is near some point A in Rk. Then the second order Taylor approximation of f of x gives f of x is approximately f of a plus the gradient of f at a transpose times x minus a plus 1/2 x minus a transpose times h times x minus a, where this is the gradient of f evaluated at a, and h is the Hessian of f evaluated at a. Now, let's say we want to maximize f. The Newton-Raphson method says to first pick an initial x value a, then consider the second order Taylor approximation of f of x for x near a. Okay. And that's given by this. Third, find the maximum of the second order approximation by taking the gradient of the second order approximation and setting it to 0. Letting q of x equal the second order approximation, which is this, we want to find the gradient of q of x and set it to 0. The gradient of q of x is the gradient of this plus the gradient of this part plus the gradient of this third part here. So that's what we have. Okay, f of a is constant, so the gradient is 0. And we have the gradient of this part, which is just the gradient of f at a. And the gradient of this part is h transpose x minus a plus h times x minus a. Now, why is that here? Okay, so let's see. You look at this part here. This is of the same form as b transpose x. So the gradient of this is just b. Okay, so we get the gradient of f of a. So this is a fact. The gradient of b transpose x is b. And we just took that fact and combined it with the multivariable chain rule. Okay, and the Jacobian of g of x given by x minus a, which is this part here, the Jacobian of that is the identity. Okay, so we're just using this fact here, except that instead of x, we have x minus a. Okay, so essentially, we're just using this fact. Okay, so that's why we have this. Now, what about this part? Okay. Well, the gradient of x transpose ax is a transpose x plus ax. Okay, notice this part here has the same form as this thing here. Okay, so we just applied this rule combined with the multivariable chain rule because we have x minus a instead of just x. Okay, so that's how we got this. Okay, so So now we have the gradient of f of a, the gradient of f at a plus this stuff, and H transpose is H because the Hessian is symmetric. So we have 2H x minus a. Simplify that a bit, we get this. Setting the gradient of q of x equals to 0, we get this. Now bring the gradient of f to the other side, get negative the gradient of f at a. Okay, get rid of that h by taking the inverse of h, multiplying both sides. So we get negative h inverse the gradient of f, assuming that h is invertible. Okay, now solving for x, bring that a over. And we get x equals a minus h inverse times the gradient of f. Thus, the maximum of q of x occurs at x equals a minus h inverse gradient of f, assuming that h is negative definite, because the Hessian of q is h transpose, which is the same as h. Okay, so if h is negative definite, then the Hessian of q is negative definite. So we get a maximum. Let x naught be a, and x sub t plus 1 be x sub t minus h inverse gradient of f at x sub t. Okay, so we got this from here, x being a minus h inverse gradient of f at a. Okay, that's what inspires this formula here. Okay. Here, h is the Hessian of f evaluated at x sub t. By iteration, we get a sequence x0, x1, x2, dot dot dot, which should converge to the x value that maximizes f. To summarize the multivariate Newton-Raphson method, suppose f from Rk to R is twice continuously differentiable. 1. Pick an initial value x naught equals to a. 2. Let x sub t plus 1 be x sub t minus h inverse times the gradient of f, evaluated at x sub t, where h is the Hessian of f evaluated at x sub t. Third, f attains a max at the x value to which the sequence converges.